constant, and other is stepwise equilibrium constants, and they are related to each other. We discussed it yesterday. Now, let us go to the presentation directly and discuss the. Now, the complexation process, the stability factor is a very important factor in, particularly when you will read in the next semesters the use of complexes in analytical chemistry, how the metal ions are estimated or detected by complexation process, and obviously stability plays a crucial role in that process. Similarly, the biological use of the coordination complexes, the metal complexes are extensively used they are part of many enzymes, and now they're part of many drugs also. So it is the complexation process with the different bioligands that also plays the stability of those complexes also plays a crucial role in the application of the metals in the biological system. So we will talk about these things. uh, स्क्रीन मेरा शेयर हो गया?
No, sir.
नहीं?
No,
No,
sir.
sir.
No, sir.
No, just wait. Slides are visible or not?
No, sir.
No, sir.
No, sir.
Yes.
Yes?
No, sir.
No.
No, sir. No, sir.
Okay, let me try once again. Now, is it okay?
Now visible, sir.
Yes, sir.
Is it okay now?
Yes, sir.
Yes, sir.
Okay. So, stability constants of metals are extremely important. As I was saying, that it is they play crucial role in analytical chemistry. Different metal ions or part of the important complexes for estimation of the metal ions, and they also have important role. The stability of the complexes have important role in the biological systems also, where metals are integral part of many enzymes and also now many drugs. So complex reaction, as I said, can be viewed as substitution reaction, where solvent is stepwise replaced or displaced by the ligand, and number of water molecules is not always same as the number of ligands added. For example, most of the metal ions, when hydrated in water, they form hexa aqua, this type of complex. But many times when you add ligand to such a system, the complex that originates from in such an hexa aqua metal complex, the resulting complex may have only 4 ligands. It may be square planar or it may be tetrahedron. So all water molecules are displaced, but then incoming ligands are only 4. So these type of situations happen. The number of water molecules replaced is not same as the number of ligands added. So then we have, if the ligand is capable of acting as a bridging ligand, we can have a polynuclear complex, a hydrated cation, hydrated cobalt 2 plus. When you add a ligand to it, which has the capability to act as bridge, simultaneously bind itself to the two metal ions, then the resulting complex can be a binuclear complex. It can be a dinuclear, trinuclear, we call it generally polynuclear complex, provided the ligand has this capability of bridging the two metal ions. So that's one complicated situation that may arise during the complexation. The second complication that can arise is that sometimes all water molecules need not to be replaced, or two different kinds of ligands get attached to the to the metal ion. So some water molecules are remain attached, and some new ligands are added, or two different kinds of ligands get attached to the central metal ion, and we call such complexes mixed ligand complexes. So that sort of situation is also encountered in different situations. Then we discussed yesterday that the extent of complex formation, the extent of reaction, or extent of stability of the complex is measured by two equilibrium constants in the solution state, that is known as overall equilibrium constant, overall stability constant, and stepwise equilibrium constant, or stepwise stability constants. The overall stability constants are designated by beta, and the stepwise equilibrium constants are designated by big K's. So beta 1, when the first only one ligand has been added to the metal, so we call it beta 1, or beta 1 and K1 are same. But when you go to the second step, beta 2 is equal to K1 and K2, because K1 is equal to ml m into L, but K2 is equal to ml2 ml into L, and you substitute the value of ml from this upper equilibrium constant. Ml is equal to Km into L. So if you substitute the value here, Kml, then it becomes K1 K2 into the equilibrium, into the concentrations, and ml and ml go out. So similarly, B3 is equal to K1 K2 K3, and B4 is equal to K1 K2 K3 K4, and you can write beta n equal to K1 into K2 into K3 into K4 up to the Kn. So that is the relation between the stepwise equilibrium constants and the overall equilibrium constant. The stepwise equilibrium constant only talks of a particular step, whereas suppose K2 talks about the extent of formation of ml2 only. And what about the previous step, the first step? It's not bothered about that step. But beta 2 will take into consideration both the first step and the second step. All the steps which were previously happening before K2, they are also taken into consideration. That's why beta 2 is equal to K1 into K2. Similarly, K3 is only concerned with the third step, but beta 3 involves all the steps which had taken place before third step. So it is equal to K1, K2, and K3. That's fundamental difference between stepwise equilibrium constant and overall equilibrium constant. Now, beta 4 is likewise this, and beta 1 is like this. And Kn is equal to mln, mn, n minus ln minus 1 n into L. So ml value from the first equilibrium constant. What is ml? It is K1 m into L. Similarly, what is ml2 concentration? It is K2 into cross multiply ml into L. These values are written here. So K1 is equal to this, ml is equal to this, ml2 is equal to K2, ml this, and this. Then substitute the value of ml from the first one. So you get K1, K2, m into L2. Similarly, ml3 is equal to K1, K2, K3, m into L raised to power 3. So ultimately, mln n times is the final product is equal to K1, K2 up to the Kn m into L raised to power n. Then you write beta 1. Beta 1 is ml divided by m into L, that's equal to K1. What about beta 2? It is ml2 m into L square. So you substitute the values here, you get K1 into K2. Similarly, beta 3 becomes K1, K2, and K3. Beta n becomes mln divided by m into L raised to power 3. You substitute the value of this mln. It is K1, K2 up to raised to power n, Kn, m into L raised to power n. So m into L raised to power n is in the denominator also. That gets cancelled. You get only K1, K2, and up to the level of Kn. So this is how the two equilibrium constants are related to each other. Then if you take logarithm on both sides, so it becomes like this. This also we discussed yesterday. Log beta n is equal to summation 1 of n varies from 1 to n log of Kn. Now, equilibrium constant is related to the thermodynamics. Equilibrium is a property of it can be linked with the thermodynamics. That's why these stability constants are also known as thermodynamic stability constant. They are also called formation constant, and formation heat or formation or free energy of formation. These are thermodynamic terms. So delta G zeros, the change in free energy under standard conditions, is related to the equilibrium constant like this, minus 2.303 or T log of beta n. So then you know the delta G is equal to delta H in minus T delta S, where the delta H0 is the standard enthalpy change and delta S is standard entropy change. So if substitute the values here, so the minus 2.303 r log of beta n becomes equal to delta H by T minus delta S, right? So then if you know the value of the delta H and delta S, and you know the temperature at which the reaction has happened, you can calculate the value of the thermodynamic the overall stability constant of the complex. For ionic ligands, if the ligand is ionic, delta H in the aqueous solution is huge. It is plus minus 20 kilojoules per mole. So there is a lot of heat either generated or absorbed during the reaction, during the complexation process, if the ligand is also ionic. For neutral monodentate ligands, if the ligand is neutral and it is monodentate, then delta heat change, heat of the enthalpy change is very small, plus minus 0.20 kilojoules per mole. And for polydentate ligands, if the ligand is forming a chelate ring around the metal ion, then the delta H is huge. It is goes up to the minus 85 kilojoules per mole. So delta S, the entropy during complexation, is most of the times positive. That is, it is favorable. Why? Because effect of the ligand binding more than offset by the release of solvent molecules from the coordination sphere. What happens during the complexation process? That ligands are organized. There is decrease in entropy. If you look at the situation from the ligand point of view, because ligands are now organized, there's less disorder in the energy of the ligands. They are organized now. Whereas if you look at the situation from the metals point, whereas if you look at the situation from the water molecules that get released from the coordination sphere, that randomness is that generates more randomness, and solvents are more most of the time they are more freely to move, and that generates more entropy than the decrease in entropy that occurs by binding of the ligand to the metal. I'll say it again. When the ligand gets bound to the metal, entropy is expected to decrease, but that decrease in entropy is more than compensated by release of water molecules from the coordination sphere. So overall, there is a positive change in the entropy. Entropy change is positive. And second thing is, many times the ligands are negatively charged, and when they bind with the metal ion, they neutralize the charge. The positive negative charge combine and they neutralize the charge on the metal. So charge neutralization on metal decreases solvent dipole and interaction. This results in decrease in the solvent dipole ion interaction. And when metal was earlier, when metal was serving as a positive charge center in a solution, the dipoles, the dipoles of the water molecules were all oriented in such a fashion that oxygen, the negative end, was heading towards the metal, and positive end head was heading away from the metal. So when the charge on the metal becomes neutralized, metal no longer is a positive center. If the negatively charged ligand gets attached to it, then this sort of orientation of the water molecules diminishes. And when this orientation diminishes, there is more disorder. And when this disorder increases, then the entropy increases. So that is also another source of increase in entropy. So delta S is of the order of 10 joules per Kelvin per mole for neutral molecules when the ligand is neutral, and it is of the order of 80 to 260 kilojoules per Kelvin per mole for polydentate ligands, and S increases with higher charge on the ionic ligands. As the ligand becomes more charged, the entropy becomes more favorable and higher number of donor atoms. If the ligand is polydentate, it has more than one donor site, then it can form a ring around the metal ion, then the entropy increases with a large amount, right? So these are the factors which favor the stability constant. The thermodynamic and kinetic stabilities. The thermodynamic stability of the complex is measured by the bond energy, the stability constants, and redox potential. These are the physical variables, physical parameters, which are used to judge to what extent the metal complex is stable, or to what extent the equilibrium constant has the numeric value. Larger the numeric value, larger is the stability of the complex, and bond energy is an important parameter. Obviously, stronger the bonds, more will be stability of the complex. Weaker the bonds, lesser will be stability of the complex. And second factor is stability constant, which is also an indicator to tell you if the complex is stable or not thermodynamically. And third is redox potential. What is the redox potential of the free metal ion, and to what extent that redox potential has changed when the metal becomes complex to a ligand? That is also an important indicator to tell you whether the complex is stable or not. If the complex undergoes easily a reduction or oxidation, that means it is not so stable. Similarly, there is another stability which is known as kinetic stability, which is the measure at which a complex undergoes reactions, substitution reactions, or the redox reactions. Then the rate and mechanism of the reaction are the important parameters which are used to judge whether a complex is kinetically stable or thermal or not. So whether it is involved in the formation of intermediates or not, what is the activation energy for a particular reaction, substitution or redox reaction or decomposition reaction. So these parameters tell you about the kinetic stability of a complex. If the activation energy is very high, then the complex is kinetically stable. If the activation energy for a particular reaction is low, then we say that the complex is very reactive. It is not kinetically stable, it is kinetically unstable. Similarly, if there is tendency to form an intermediate, reactive intermediate quite easily, then we say again it is kinetically unstable. And if it is not having a tendency to form a kinetic intermediate, we will say that it is kinetically stable. So stability constants are related to the equilibrium constant. The tendency to exist under equilibrium condition is directly related by the metal bond ligand bond energy. That is thermodynamic stability constant. So a complex which reacts quite easily, which has lower activation energy and therefore forms an intermediate quite easily, is known as labile complex. So, and that complex which has long lifetime, which reacts but then reacts very slowly, the lifetime is long, then it is called the kinetically stable complex, or we call it inert complex. So the terms inert and labile complexes, they are not thermodynamic terms, they are kinetic terms. In this, they are used in loosely in the sense that if a complex reacts quite easily, quite rapidly, the time factor is as an important factor here, that if the complex reacts in a short time without any catalyst or without any refluxing process, etc., then we say it is labile complex. And a complex which is inert, which reacts slowly, so that complex may be called kinetically inert. But if a complex is reacting slowly, that does not mean it is thermodynamically stable. Maybe it has higher activation energy only, but ultimately the product formed will be more stable than the initial complex. Then the complex is not necessarily thermodynamically stable, but it is kinetically stable, and therefore any inert complex need not to be called a stable complex, thermodynamically stable complex. Thermodynamic stability is a different ball game altogether, and kinetic inertness is altogether a different concept. So kinetic inertness is related to the rate of reaction, how slowly or how fast the substitution or redox or decomposition reaction takes place. If the reaction is sluggish, it is slow, we call it inert complex, but that does not mean it's a thermodynamically stable complex. So every inert complex is not a stable complex. That is the point. So kinetic aspects of the complex is the ability of the complex to engage itself in a reaction involving replacement of one or more ligands in coordinations paired by another ligand is called stability of the complexes. There are some complexes that undergo rapid substitution. They are known as labile complex. And those reactions which do this substitution process quite slowly, we call them inert complex. So this is the concentration of the metal when a metal and ligand have been added into a solution. The overall concentration of the metal, some metal may be in the free state, some metal may be in the form of Ml, plus some metal may be formed of Ml2 plus Ml3 up to the Mln. So M has the total concentration of M will be distributed into different components. There will be free metal and there is complex metal. And in the complex metal, we have different situations: Ml1, Ml2, Ml3, Ml4, and ultimately, his Ml6 is the highest coordination, the stable coordination, Ml6 up to Ml6. Similarly, the concentration of the ligand is free ligand plus Ml plus 2 times Ml2. So it is because ligand is here part of the complex, so 2 times, similarly plus n times. So trends in the stepwise stability or formation constant. This we were discussing yesterday, that most of the time the stability constants follow the trend. K1 has larger value, then there is progressive decrease in the value successive steps. The value stability it forms
You are
cadmium
not audible.
complex. Hello, क्या बोल रहे हो? Okay, अभी आ रही है?
So,
Okay. Cadmium ammonia and cadmium cyanide complexes we are taking as examples to illustrate our point that the stepwise equilibrium constants follow a trend. Okay, first, the equilibrium constant for the first step has the highest value, and then successive steps have lower value. The stepwise equilibrium constants diminish as we proceed from first step to the highest, the larger, the other steps. So tiny complex, and cadmium 2 plus getting bonded to a nionic ligand cyanide and forming a 2 negative complex, right? So cadmium plus ammonia forming the first step. In the first step, cadmium, I should have written here K1. So K1, the magnitude of the K1 is 10 raised power 2.65. And the next step, cadmium ammonia complex reacts with another molecule of ammonia. You get cadmium ammonia 2 plus. You can see the equilibrium constant for the second step is bit lower than the first step. It is 2.10 raised power 2.10. Similarly, cadmium 3 third step has 1.44 value, right? Ideally, I should have written in the first step cadmium hexaaqua 2 plus. In the second, the complex that is formed here will be cadmium monoamine amine 1 and water 5 times. And here it would be 5 times water and 1 amine reacting and forming two amines and two amines and 4 water molecules. Then this will be forming 3 water and 3 amines molecule, 3 amine molecule. And fourth one next will be 4 amine all water molecules getting lost. So fourth is this one. So there are the 4 coordinated complexes formed, and you have 4 successive stepwise equilibrium constants, and last one has very low value 0.93. So beta 4 overall equilibrium constant is equal to 1 K1 into K2 into K3 into K4, and you multiply them. The bases are same, powers will be added. So this is beta 4 is 10 raised power 7.12. So it is quite a stable complex, but not as stable as the cyanide complex. Look at the cyanide situation. The first is 5.48, second one is 10 raised power 512, third one 4.65, fourth one 3.55, and beta 4 is 10 raised power 18.8. So this tells you, if you compare the overall equilibrium constant or stability constants of the cadmium tetraamine complex and cadmium tetracyano cadmium complex, the cyanide complex has much higher stable, almost 3 times more stable than the cadmium amine complex. So steady decrease, that is gradual decrease in the stepwise formation constants, or what are the reasons why should K2 always less than K1 and K3 less than K2 and K4 less than K3? What does this happen? So it is the probability of the replacement of the water molecule decreases. This we discussed yesterday also, that in the first situation, in the first step, there are 6 water molecules, and out of those 6 water molecules, any water molecule can be replaced by the ligand. In this second situation, there is only one ligand, and there are only 5 water molecules, and they need to be displaced by the ligand. So the probability of the displacement decreases, and therefore that decreases the extent of the reaction, the degree of the formation of the complex decreases. And there are electrostatic factors, as we discussed. If the ligand is negatively charged, it neutralizes the charge of the metal ion, and the attraction of the metal center with the negatively charged ligands diminishes at every step, and therefore we expect that the formation constant of the successive steps should be lesser. So then there are steric hindrances. Suppose your ligand is bulky and it got introduced into the complex, then it will not allow the other ligands to come near to the metal. So that decreases that steric hindrance diminishes the chances of the other ligands to get attached to the metal. So there is progressive decrease in the stability constant of the complexes. Then there are exceptions, that sometimes it is not the trend is not uniform. Many times we find that the Kn plus 1, that is, say K4 greater than K3. This happens in many times. So what are the reasons for that? There is unusual structural change. This we were discussing yesterday, that there is unusual structural changes happening. And one structure change was crystal field stabilization energy, which we were discussing yesterday, that this is the stability provided to the complex. This is unique situation in the complexes. It does not, this crystal field stabilization energy is not We don't see it in anywhere except in the coordination complexes, because this is the stability provided to the coordination complex, not by the bonding electrons, which is the generally the argument is that bonding electrons provide the stability to the complex, to any molecule. Stronger the bond, stronger stable the situation, stable more stable the molecule. And here, in the crystal field stabilization energy, this extra stability is provided by non-bonding electrons. Those electrons which have not participated in the bond formation, they are not expected to play any role in the bond formation. Yet they, because of their distribution in the non-bonding orbitals, they give extra stability to the molecule, and that extra stability is called crystal field stabilization energy. And for example, let us take the example of iron. Iron 2 plus. Iron 2 plus has 6 electrons, and they are to be distributed into two sets of orbitals. One is the if it's an octahedron complex, one is the T2G, and other is the EG set. T2G is having lower energy, minus 0.4 delta 0, and EG orbitals are raised in energy, as if you compare it to the barycenter, and that raising of energy is plus 0.6 plus 0.6 delta 0. So there are 4 electrons in the, if it is a high spin complex, say you have used the ferrous sulfate salt added to the solution. So it has formed the Fe, ferrous sulfate will form FeH2O 6 times, 2 plus, and sulfate will remain outside. So it will form an aqua complex. There are, because water is a weak ligand, the d orbitals or not the splitting in the d orbital is not so high. D6 system, iron is in plus 2 oxidation state. And if you calculate the crystal field stabilization energy, 4 into zero point 0.4 is 1.6, and that becomes
So you are not audible, sir.
सर आपकी आवाज नहीं आ रही है।
शायद नेटवर्क इशू होगा, वेट कर लेते हैं थोड़ी देर। सर लेफ्ट हो गए। स्क्रीन विजिबल है?
हेलो, कौन बोल रहा है?
वो तो आपकी आवाज नहीं आ रही, लेफ्ट हो गया।
सर आपकी आवाज ही नहीं आ रही।
आवाज नहीं आ रही?
सर आप लेफ्ट हो गए थे मीटिंग से।
नहीं तो अच्छा यार, ये इंटरनेट हो गया। अभी हूं मैं। अभी आप मेरी
यस सर।
आवाज आ रही?
Yes,
सर बट
Yes,
स्लाइड्स
sir.
विजिबल नहीं है सर।
स्लाइड विजिबल है?
No, sir.
No,
no,
sir.
नो
sir.
सर।
No, sir.
ओके, ठीक है, आपने पॉइंट आउट किया, मैं दोबारा करता हूँ। मैं इसको
सर स्टार्टिंग में भी कट रही थी, बीच बीच में कटती जा रही है।
यार अपने से इन्होंने यहाँ फाइबर लगाया हुआ है, तो अब क्या पता ये फाइबर भी क्या कर रहा है। ऐसी मुसीबत ये है। मैं दोबारा करता हूँ। जब ऐसा होता है तो इमीडिएटली आप पॉइंट आउट किया करो। मुझे आवाज नहीं आई ना?
सर आप लेफ्ट हो गए थे मीटिंग से, सो इसलिए आपको सर आवाज नहीं आई।
ओके, ये तो बड़ी मुसीबत है। अभी दिख रहा है स्लाइड?
Yes, sir.
Yes, sir.
यस सर।
मैं दोबारा उस स्लाइड पे जाता हूँ। हाँ, ये तो हो गया था। वी वर हियर। हम यहाँ पे, मैं बता रहा था, मैं दोबारा बोलूंगा कि आयरन जो है, आयरन 2+ वाटर के साथ आपको कंसेप्ट होगा ना कि हाई स्पिन लो स्पिन कॉम्प्लेक्स का कंसेप्ट है।
Yes, sir.
आवाज मेरी आ रही है?
Yes, sir. आ
यस
रही है.
सर।
हाँ, हाई स्पिन और लो स्पिन का कंसेप्ट है ना कि अगर लिगेंड बहुत वीक हो, लिगेंड्स हैव बीन अरेंज्ड इन सीरीज, दैट सीरीज इज नोन एज स्पेक्ट्रोकेमिकल सीरीज, है ना? ये आप जानते हैं?
सर आपकी आवाज नहीं आ रही है फिर से।
सर आपकी आवाज नहीं आ रही।
अच्छा, मैं अभी चुप हूँ यार, आवाज कैसे आएगी? अभी आ रही है?
यस सर।
यस सर।
मैंने अभी वो अपना स्लाइड से वापस आ गया मैं। लेकिन किससे इंटरेक्ट करूं? मैं ऐसे बोल रहा हूं कि भाई D4 से D7 तक ये 4 कॉन्फ़िगरेशन ऐसी हैं, D4, D5, D6 और D7, जिनके पास
सर आवाज नहीं आ रही है।
सर
सर
आवाज
आप ऑडिबल नहीं हो।
सर मीटिंग में है या चले गए?
पता नहीं।
सर को एक बार ही बता दो, ऐसे सर को लग रहा होगा कि शायद मैं मीटिंग में हूँ।
हेलो
हाँ जी
Yes,
सर।
sir.
हेलो,
हाँ जी सर।
मेरा नेट चला गया था, मैं वापस आ गया हूँ।
जी सर।
एवरीबॉडी इज हियर ना?
यस सर।
यस सर
यस सर।
ठीक है, तो अगला पीरियड किसका है?
सर टाइम टेबल चेंज हुआ है सर, अभी देखना पड़ेगा।
हेलो, आवाज आ रही है?
यस सर आ रही है आवाज।
ठीक है, तो मैं बोल रहा था कि अगर स्प्लिटिंग बहुत कम हो और पेयरिंग एनर्जी ज्यादा हो तो फिर हाई स्पिन कॉम्प्लेक्स बनता है। एंड इफ इट इज रिवर्स, दैट splitting has occurred huge, splitting between T2G and EG orbital is large, then the low spin complex is formed, that electrons are forced to pair in the T2G and rather than going into the EG orbitals. Now, who decides this? It is the strength of the ligand primarily, which decides whether the complex will be high spin or low spin, and also the nature of metal and the charge on metal has also a role to play here, right? तो ये क्यों बनता है, कैसे बनता है, दैट्स नॉट आवर डिस्कशन। अभी हम एक एग्जांपल ये साइट कर रहे हैं कि हमने बोला कि जो स्टेप वाइज इक्विलिब्रियम कांस्टेंट्स है, जनरल ट्रेंड ये है कि वो शुरू वाला जो इक्विलिब्रियम स्टेप वाइज इक्विलिब्रियम कांस्टेंट वो उसका वैल्यू ज्यादा होगा, एंड इट प्रोग्रेसिवली डिमिनिशेस इन मैग्नीट्यूड for the reasons that we cited, that there may be steric crowding created by the ligand which already enters and then does not look at the and when they bind to the metal, they diminish the positive charge which was on the metal, and because of that positive charge, ligands were getting attracted to the metal. Because that positive charge has diminished, therefore the attraction between metal and the ligand decreases, and therefore that decreases the successive stepwise equilibrium constants. Now I am saying that uh, the many times there are exceptions also when the stepwise equilibrium constants do not follow this general trend, that the K4 has higher value than K3, K5 has higher value than K4. This type of situation is encountered. Obviously, we need to justify them. We need to find the reason why this happens. One of the reason is that there is structural changes, electronic changes during the complexation process. We have an iron hexa aqua complex which is formed by when you dissolve any iron 2 plus salt in water, it immediately forms iron hexa aqua complex. And if you add to it the bipyridine ligand, which is a strong field ligand, and water is a weak field ligand, and it ultimately forms this complex when all water molecules are replaced, 6 water molecules are replaced by 3 bipyridine, because bipyridine happens to be a bidentate ligand. You get ultimately this tris complex of bipyridine. This is low spin complex, and iron complex is a high spin complex. You got my point? In other words, there is no unpaired electron because iron has 6 electrons in the d orbital non-bonding. All those non-bonding electrons are paired up in the T2G set, and there is no unpaired electron in the hexa in the tris bipyridine complex. So it's a diamagnetic complex. Whereas in the case of hexa aqua complex, there are 4 unpaired electrons because 4 electrons are placed in T2G, 2 electrons are placed in EG. So there are 2 unpaired electrons in the EG and 2 electrons unpaired in the T2G also. So overall there are 4 unpaired electrons. Now what happens that when you start the reaction. This is iron hexaaqua complex, which is in the high spin state. You add bipyridine. One bipyridine molecule will knock out two water molecules and form this mixed ligand complex, where there are four water molecules linked to the iron, and two bipyridine molecules have been added and no, one bipyridine molecule has entered the ligand and got, occupied two coordination sites because this is a bidentate ligand. So this complex still remains a high spin complex because there are four water molecules and there's one bipyridine. Then you do the second step, which is designated by K2. Then another molecule of bipyridine enters, and two more water molecules are displaced. This is also high spin complex. This is a mixed ligand complex. There is strong field ligand and there is a weak field ligand. They sort of counterbalance each other. एक बहुत ज़्यादा strong है और एक बहुत ज़्यादा weak है. In the third, if you look at the relationship between K1 and K2, K1 has larger value than K2, and that is what we expect in the normal circumstances, that successive equilibrium constants, stepwise equilibrium constants follow a trend that K1 must be greater than K2. That's observed here. In the third situation, when the left out two water molecules are displaced by the bipyridine, you get a pure bipyridine complex, which is totally a strong field low spin complex. So here is transition from high spin to the low spin, and this complexation, the crystal field stabilization energy for the high spin state, if you calculate 4 electrons in the T2G, that gives minus 1.6 delta 0, 2 electrons in the EG, that gives 1.2 plus 1.2 because the orbital is 0.06 plus 0.6 higher energy. So the overall crystal field stabilization energy in the high spin state is minus 0.4 delta 0. But if you have a low spin complex, tris bipyridine, all the 6 electrons are placed in T2G. So 6 into 0.4, it is 2.4, minus 2.4. So there is huge increase in the crystal field stabilization energy in the case of low spin complex. And because of that extreme stability, the K3 has larger value than the K2. So the trend is K1 larger than K2, but then K3 larger than K2. This exception happens because of transition of the high spin to the low spin in the third step, and that generates this upset in the numeric value of the equilibrium constant, right? This has must be written. Yes, iron. This is the first formed in the first step. This is formed in the second step. Both of them are high spin, and they have configuration T2G4, EG2. Crystal field stabilization is 4 into 0.4 plus 2 into 0.6 delta 0. That becomes minus 16 plus 1.2 minus 0.4 delta 0. In the case of tris bipyridine iron complex, crystal field stabilization is T2G6, EG0, that is 6 into minus 0.4, that is minus 2.4 delta 0. So compared to minus 2.4 and 0.4, there is huge increase. That's why K3 has larger value than K2. But look at the other example, cadmium bromide. There are 4 steps that you add the aqua complex, cadmium hexaaqua. You add cadmium salt to water, it forms cadmium hexaaqua. And the product formed is when you add bromide to this hexaaqua solution, you get cadmium tetrabromo cadmium 2 complex, right? So the first step is here displacement of one water molecule by bromide. So you have a K1 which has large value. The second step is again another water molecule displaces another. This should have been bromide here. Sorry, this is bromide here and displacing another water molecule, getting dibromo. K2 is less than K1. That's expected and it's good. And go to the third step. K3, another. Again, it's wrong here. It is bromide negative. So another bromide enters and another water molecule leaves, and you have tribromo triaqua complex. And in the fourth step, another bromide enters and now 3 water molecules are lost because this is the ultimate complex. So this K4 has larger value than K3. It should have been smaller value. So there is unusual structural and electronic configuration changes in this fourth step because 3 water molecules are lost and complex reverts from hexa coordinated for octahedron configuration to a tetrahedron configuration. So there is structural change, there is electronic configuration changes. That's why K4 has larger than value than K3. So these are the reasons why this upset happens. That there is unusual structural changes and there are changes in the electron structure of the metal. That is, there is change in crystal field stabilization energy, and generally the thumb rule is more the crystal field stabilization energy, higher will be the stability constant or formation constant of the complex. Right? So now the next is formation function. So average coordination number of ligand per metal ion is known as the formation function. It is defined as what is the total concentration of the ligand that is bound to metal divided by total metal ion. So it is the concentration of the ligand which is bound minus concentration of the ligand which is not bound, which is free, divided by concentration of metal. That is known as formation function. It's a parameter which is frequently used, which is designated as n dash. That is known as how many ligands are bound to the metal center per metal center. So total number of total concentration of the ligand which is bound minus total concentration of the ligand which is free divided by total concentration of the metal. That gives the formation function. So Cl minus Cl dash ligand not bound divided by Cm. So how you write the concentration of the ligand, total ligand? That is L, the free ligand, total concentration of the ligand. That is free ligand plus the ligand, which is in the part of the complex, Ml plus Ml2 plus Ml3, Ml n times Ml. So 2 times because 2 ligands were there, 3 times with 3 ligands were part of this complex, and n mln minus L minus the ligand which is free. Right, this is total concentration of the ligand, and this is the free ligand. So this L and this L will cancel out, minus divide by total concentration of the M. M is either free or the Ml or the Ml2, Ml3, Ml4, like this. So the numerator becomes L and L goes, where Ml to 2 ml2 this like this divided by M. So it is summation of n is equal to 1 to n mln, because this is 1 into ml, 2 into ml2, 3 into ml2. So write generally n into mln divided by summation of n 0 to 1 m mln. So n0 means when the nl is 0, because m also appears there. So what is the ml, concentration of ml? It is equal to 1 k1 m into l. This we saw in the previous slide, and this is equal to beta 1, because k1 and beta 1 are identical, m into l. ml2 is equal to k1 into k2 m l square. This is beta 2 m l square. mln is equal to k1 k2 kn m ln. So this is beta n m. This we studied in the previous slides. So therefore eta dash, if you substitute these values here, these values ml, in place of ml I will write beta 1 m into l. In place of ml2 I will write beta 2 m into l square. In place of mln I will write beta n m l raised to power n. So you substitute these values there. So this is the equation: beta 1 m into l, 2 beta 2 m into l square, like this. So numerator in the denominator again we have write the same, beta 1 ml, like this. So it is beta 1 L, because m gets cancelled. M, you take m common, so this is beta 1 L. M is common in every term in the numerator. Similarly, m is common here also. So m gets cancelled. So this is beta 1 L, 2 beta 2 L.
You are not audible.
सर आपकी आवाज बहुत कट रही है. ਜਿਹੜਾ ਤੇ ਝੋਲਾ ਤੂੰ ਤਿਆਰ ਕੀਤਾ ਨਿੱਕਾ ਜਿਹਾ ਕਹਿੰਦਾ ਕੁੜੀ ਵੀ ਤਿਆਰ
क्लास हो गई क्या खत्म?
टाइम
सर
तो
ने
हो
तो
गया।
लीव कर दिया है।
दैट्स व्हाई आई गेस सर को लगा होगा कि टाइम भी हो गया है।
1 o'clock भी हो गया, लीव कर देते
बट
हैं।
ये क्या पता सर को कि हमें सुनाई नहीं दे रहा है उनका। वापस तो नहीं सर ने ज्वाइन करनी है मीटिंग?
पता नहीं, ऐसे तो बताकर ही जाते हैं हमेशा।
एक बार सीआर ग्रुप में मैसेज कर लें सर को।
I have already forwarded the text to sir. Wait कर लो please.
श्योर।
क्लास खत्म हो गई।